Hello everyone. We've introduced the time domain analysis of dynamic circuit systematically in previous 3 weeks. From this week on, we will introduce the sinusoidal steady-state SSS analysis of dynamic circuits. We will introduce sinusoids in the first lecture. Firstly, sinusoid has 3 elements. Let's take the voltage and the current of a resistor as examples. Generally speaking, the voltage and the current can be expressed in the form in the figure. From the expressions, we can see that the first element of voltage and current is the amplitude. The amplitude of the current is Im. The amplitude of the voltage is Um. The subscript M means maximum. The second element is the angular frequency. In the Principles of Electric Circuits course, the voltage and the current have the same frequency. Their angular frequencies are both omega. The relationship between the angular frequency and the frequency is omega equals 2 pi times f. The relationship between the angular frequency and the cycle is omega equals 2 pi over capital T. Besides, this part of the sinusoid is called the phase. Phase is a function of T. In other words, angular frequency is the time rate of the change of the phase. This point will be discussed in the future communication signal processing course. The third element is the initial phase angle. The initial phase angle of the current is psi I. For the voltage is psi U. We need to point out that a sinusoid can be expressed by both sine and cosine. Most textbooks in China use sines to express sinusoid, but most textbooks in Western countries use cosine. In the following lectures, you will find that the result of SS analysis are the same whether you use sine or cosine. By adding 90 degrees to the phase of sine, it becomes cosine. So there's no essential difference between sine and cosine in expressing a sinusoidal excitation. Next, let's discuss the initial phase angle of a sinusoid in detail. This is a waveform of a current sinusoid. You see, if psi equals 0, it's a sinusoid whose initial phase angle is 0. It's a special sinusoid and can be expressed as I equals Im times sine omega t. If the initial phase angle is 90 degrees, the waveform of the sinusoid is like this: I equals Im times sine omega t plus 90 degrees. In fact, it equals Im times cosine omega t. This confirms the statement above that the difference between sine and cosine is 90 degrees phase difference. The third condition is like this. This waveform not only can be expressed as it equals Im sine omega t plus 270 degrees, but also Im times sine omega t minus 90 degrees. In fact, they are the same. In this course, there's a rule that the absolute value of the initial phase angle must be no greater than 180 degrees. We always use this form expression instead of this form. After 3 elements of sinusoid, let's discuss the phase difference between 2 sinusoids with the same frequency. Take voltage sinusoid and a current sinusoid as an example. This part of a sinusoid is phase. If 2 sinusoids have the same frequency, their phase difference is a constant value. The phase difference between 2 sinusoids with the same frequency is the difference between their phases. The phase difference of the 2 sinusoids equals psi u minus psi I. Their waveforms are shown in the figure. According to the previous discussion, psi u here is greater than 0, and psi I here is less than 0. For these waveforms, psi u minus psi I is greater than 0. In this condition, we call u leads I, or I lags u. When the phase difference psi phi is less than 0, it means I leads u or u lags I. Next, let's introduce the method of judging who leads who from the waveforms. From the waveform, we don't need to first judge whether the initial phase angle of the sinusoid is greater or less than 0. We can judge who leads who directly from the waveforms. The key is focus on the points with the same phase. The 0-degree phase of the voltage is here. The 0-degree phase of the current is here. Coming from the negative to the positive of the time axis, we first meet the 0-degree of phase of voltage point and then the 0-degree of phase of current point, so we can judge U leads I. Similarly, we can focus on 90-degree phase of voltage and 90-degree phase of current. 90-degree phase of voltage leads 90 degrees phase of current. Of course, we can also define the 0-degree phase of current here and the 0-degree phase of voltage here, so I leads U in this condition. There's no problem. Because the cycle of all sinusoids is 360 degrees. But in the following discussion, we will define the maximum of the phase difference. So U leads I in this figure. Next, we will discuss three special phase relationships. First one is in phase. From the waveform, you can see the voltage and the current pass through the same phase point at the same time. The second is opposite phase. At this time, voltage passes through 0-degree phase point and the current passes through 180 degrees phase point. Similarly, at this time, the phase of voltage is 0 degree and the phase of the current is minus 180 degrees. In the third condition, U leads I 90 degrees, or I leads U 270 degrees. According to the discussion on initial phase angle, the maximum of initial phase angle and the phase difference must be no greater than 180 degrees.